The assumption is simple. Infrastructure as code makes you faster, removes the guesswork, eliminates drift. You adopt it because the alternative, clicking around in the Azure portal, manually documenting changes, hoping someone remembers why a resource was configured that way, is untenable at scale. And when you choose your tool, the choice feels obvious. Terraform sits there as the industry standard. Cloud agnostic, 20,000 modules. If you want to support multi-cloud, you pick Terraform. Or you pick Bicep because it's native to Azure, built by Microsoft, integrated with ARM, day zero support for new services. But there's a layer beneath that choice that nobody talks about, a structural layer. Because the real trap isn't which tool you pick, it's the model behind the tool, the operational philosophy, the assumptions baked into how the tool thinks about infrastructure. One model says, you maintain an explicit record of what exists and who changed it. The other says, ask the cloud what's there right now. Those models have profoundly different consequences. They create different costs, different security postures, different governance requirements, different skill needs, and most organizations choose their tool without ever examining the model underneath. This is where it breaks. The state file as a database you didn't plan for. Terraform's state file is fundamentally a database. It records what Terraform believes exists in your Azure environment. Every resource ID, every configuration attribute, every dependency. When you run Terraform plan, Terraform is asking a very specific question. What's in my state file and what do I need to change to match the code I've written? The state file is Terraform's memory. But here's the problem that nobody leads with when they're pitching infrastructure as code. That memory has to live somewhere. It can't just exist in your laptop, so you set up an Azure storage account to hold it. You enable blob versioning so you can recover if something breaks. You add a lock table in Azure Cosmos or blob storage leases so that when two people run Terraform simultaneously, they don't both try to apply changes at the same time and corrupt the file. You encrypt it, you restrict access, you set up backup and disaster recovery. You've built infrastructure to manage the infrastructure manager. And that infrastructure has operational overhead, it has cost, it has failure modes, it requires governance. Someone has to monitor the state backend. Someone has to respond when blob locking fails. Someone has to reconcile what's in the state file with what's actually deployed when they diverge. And they will diverge. The structural weight compounds. Add a second team, and now you have a coordination problem. Do they share the same state file? If they do, concurrent runs create contention. If they don't, you have to figure out how to prevent them from stepping on each other's infrastructure. Add a second environment, dev, staging, production, and now you're managing 3 separate state files. Add disaster recovery, and now you're managing state across regions. Add a second cloud provider, and the complexity doesn't scale linearly. It multiplies. Every team member adds friction. Every environment adds another state file to secure and monitor. Every concurrent run is a potential point of corruption. This is operational debt in its purest form. Not the kind that compounds slowly, the kind that grows exponentially with scale, the kind that forces you to hire a platform engineering team just to manage the state management infrastructure. Most organizations don't see this cost clearly because it's diffused. It's not one incident, it's 1,000 small operational burdens absorbed by the team that runs Terraform. 5 minutes here to debug a state lock that didn't clear properly. An hour there to manually reconcile state after a network failure interrupted an apply. A planning conversation about how to partition state across teams without creating chaos. None of those moments feel expensive individually, but collectively, they're the reason that organizations with mature Terraform deployments often end up with a dedicated platform team managing the orchestration layer. This architecture choice creates a specific vulnerability. The Plaintext secret problem. But operational burden isn't the only consequence of that architecture. There's a security consequence that's worse. The state file doesn't just record what resources exist. It records their configuration, and that includes values you'd never want exposed. Database passwords, API keys, storage account connection strings, access tokens, private IP addresses that reveal your network topology, SSH keys. All of it gets stored in the state file because Terraform needs that information to know what's currently deployed. Research shows that 22% of leaked cloud credentials originated from improperly secured state files. That's not a rounding error, that's a pattern, that's enough to matter. Here's where the model breaks down. When you mark something as sensitive in your HCL code, when you tell Terraform, don't print this in the console output, Terraform obeys. It redacts the value from your terminal. But the state file still stores it in plaintext JSON because Terraform needs it there to manage the resource. The sensitivity flag is just a UI courtesy, not actual protection. So your state file becomes a complete architectural map plus the credentials to everything in it. If someone gains access to your storage account, they get both. They see exactly what you're running. They see the connection strings to connect to it. They understand your entire infrastructure topology and have the keys. That's not just a technical problem. That's a single point of catastrophic failure. Most organizations respond by encrypting the state file at rest. They enable storage service encryption on the blob container. They feel safer, but encryption at rest only works if access control works, and that's where teams consistently stumble. Access control is the real problem, because state backends often live in a shared infrastructure account, because RBAC gets complicated when you have multiple teams, because we need to be able to run Terraform becomes everyone with contributor access can read the state file. And everyone with contributor access often includes people who shouldn't be reading database passwords for production systems. Teams often treat state backends with less rigor than they treat production databases. A production database has restricted access. It's logged, changes are monitored, but the storage account holding your Terraform state, that's often just sitting there in the same resource group as everything else with standard Azure access patterns. The moment an auditor asks who can read your infrastructure ledger, the answer is usually uncomfortable, because the answer is more people than should be able to. This creates a second structural problem. Your security posture depends on access control that's either weak or becomes increasingly difficult to manage as your organization grows. You can add encryption, you can add private endpoints, you can add diagnostic logging, all of it is necessary. None of it solves the fundamental issue, which is that the state file is a high-value asset that's harder to protect than most organizations assume. And compliance frameworks know this. HIPAA, PCI DSS, SOX, they all care deeply about who can access infrastructure metadata and credentials. The state file is the crown jewel of infrastructure credentials. And it lives in a system that was designed for operational simplicity, not security compartmentalization. This security burden isn't inherent to infrastructure as code itself. It's inherent to maintaining an explicit, persistent state file as your source of truth. The multi-cloud myth exposed. Here's what Terraform vendors tell you. Write your infrastructure once and deploy it anywhere. Azure, AWS, GCP. Your code is portable. Your skills are portable. Your modules are portable. You build a marketplace of reusable components that work across every cloud. That's the pitch. The reality is different. Terraform is cloud agnostic. Your code is not. When you write Terraform for Azure, you're defining virtual networks. You're specifying key vaults. You're writing rules for network security groups. You're configuring managed identities and role assignments using Azure's specific RBAC model. Every line of your HCL is Azure specific because your infrastructure is Azure specific. Now suppose you want to move that workload to AWS. You don't change the provider tag from Azure RM to AWS. You don't run a search and replace. You rewrite the entire architecture. A virtual network becomes a VPC with a different subnet model. A key vault becomes AWS Secrets Manager with different access patterns. The managed identity model is completely different. The security group syntax is different. The tagging strategy might be different. The availability zone logic is different. It's not portability. It's starting over. But here's what actually happens in practice. Organizations adopt Terraform because they want multi-cloud optionality. They want to avoid being locked into Azure. So they build and maintain Terraform code across multiple clouds. They hire engineers who know Terraform generically instead of Azure deeply. They create modules that are generic enough to work on both platforms, which usually means they're optimized for neither. They're maintaining a tool that prevents them from going deep on any single cloud. This trade-off becomes obvious when you look at feature velocity. Azure releases new services constantly, new AI capabilities, new networking patterns, new policy features. When you're writing native Azure Bicep, you can use those features on day one. Your code compiles directly to ARM. You're not waiting for anyone. With Terraform, you're waiting for the community provider maintainers to expose the new feature in HCL. Sometimes that happens in weeks. Sometimes it takes months. If the feature is niche or the maintainers are busy, it might not happen at all. You end up with two choices. Use the newer feature through raw ARM templates and lose the Terraform abstraction, or don't use the feature at all. This creates a specific architectural problem. You're choosing tool consistency over platform speed. You're optimizing for, I could theoretically move to AWS someday, instead of, I can use everything Azure offers me today. Most organizations that start with multi-cloud ambitions eventually realize they're either Azure first or multi-cloud, not both. The ones that are Azure first end up resenting Terraform because it's holding them back. The ones that are actually multi-cloud end up maintaining cloud-specific modules within the same codebase anyway, which defeats the purpose. The tools aren't the problem. The model is. When you pick Terraform, you're accepting that consistency across clouds matters more than depth on a single platform. When you pick Bicep, you're accepting that you're all in on Azure. One trade-off isn't inherently better. But most organizations don't make that trade-off consciously. They drift into it. They pick Terraform for the multi-cloud story and then never leave Azure. This trade-off becomes visible when you examine feature velocity. The day zero gap, when new features matter. Azure ships fast. The platform released 175 distinct services last year. That number includes substantial updates to existing services, new API versions, new capabilities, new resource types. On any given week, something changes. A new AI model becomes deployable, a new policy evaluation method, a new networking construct, a new compliance feature. When Azure ships something, it's available immediately. You can use it through the Azure CLI, you can use it through the portal, you can use it through ARM templates, because ARM is the control plane that Azure uses internally. Bicep compiles directly to ARM, so Bicep gets it immediately. Terraform doesn't. Terraform's Azure provider is community-driven. It's open source. It's maintained by engineers who volunteer their time. When a new Azure service ships, one of these maintainers has to notice, understand the API, write the Terraform resource definition, test it, and get it merged into the provider codebase. Then a new version of the provider has to be released. Then you have to update your local provider version to get access to the new resource. That process takes time, sometimes weeks, sometimes months. For niche features, sometimes it never happens at all. Here's what this looks like in practice. Azure releases a new AI service endpoint. You want to wire it into your infrastructure. With Bicep, you write the resource definition, compile, and deploy. It works. With Terraform, you check the Azure provider documentation. The resource doesn't exist yet. You have two choices: wait for the community to implement it, or drop down into raw ARM templates and lose the Terraform abstraction. This isn't theoretical. This happens constantly. Regulated industries care about this more than most. Compliance features ship in Azure first. If you're running Terraform, you might not be able to deploy a new compliance control because the Terraform provider hasn't caught up. Your governance team needs a policy that Azure released last month. You can't use it through code. You either use it through the portal, which means it's not IRC anymore, or you wait. The irony is sharp. Bicep is accused of locking you into Azure. And it does. You can't use a Bicep template to provision infrastructure in AWS. That's the trade-off. But the other side of that trade-off is that you get access to everything Azure offers immediately. Terraform is accused of being cloud agnostic, which it is. But that agnosticism comes at a cost. You're not locked into Azure, you're locked into a slower version of Azure. An older feature set, a lagging API surface. Which kind of lock-in is worse depends on your strategy. If you're Azure only, the answer is obvious. Terraform's agnosticism buys you nothing. You're paying for a delay. For an organization that's committed to Azure as its primary platform, that delay is pure cost. Features ship. You can't use them. Competitors using Bicep can. The organizational impact is subtle but real. Terraform teams often end up with a backlog of infrastructure improvements that are blocked on provider updates. Bicep teams just do the work. This compounds. After a year, the Bicep organization has deployed capabilities and patterns the Terraform organization is still waiting for. This gap reveals what native actually means. It doesn't mean pretty syntax. It doesn't mean integrated tooling. It means you get access to the platform the moment it ships. It means when Azure's architects build a new feature, you can immediately use it in code. It means the tool isn't the bottleneck between your intentions and the platform's capabilities. The day zero gap is a structural advantage, not a tactical one. It's the difference between using what's available today and using what was available 3 months ago when the provider finally caught up. Understanding this gap moves the conversation away from ideology and into outcomes. Bicep's stateless model, the architectural shift. The fundamental difference between Terraform and Bicep isn't syntax, it's where the source of truth lives. In Terraform, the state file is the source of truth. When you ask Terraform, what should I change? It's comparing your code against what's in the state file. The state file is the memory. The state file is what Terraform trusts. Azure is just the runtime, the place where those changes actually happen. Bicep flips this. In Bicep, Azure Resource Manager is the source of truth. When you deploy a Bicep template, you're not managing a separate artifact that remembers what's deployed. You're sending a desired state to ARM and asking it to reconcile. ARM looks at what you're asking for. ARM looks at what actually exists. ARM figures out what needs to change. Then ARM makes it happen. There is no state file. There's no separate database. There is no locking mechanism. There is no backend to secure. There is no version history to manage. There is no recovery strategy for when the state file gets corrupted. The complexity simply doesn't exist. Instead of maintaining infrastructure to manage the infrastructure manager, you're just writing code and sending it to the platform. The platform does what platforms are supposed to do. It reconciles your intent with current reality. That's its job. That's what ARM was built for. This changes everything operationally. You don't need to set up a storage account for the state backend. You don't need to configure blob locking to prevent concurrent corruption. You don't need to encrypt the state or restrict access to it. You don't need monitoring to watch for state lock timeouts. You don't need incident response procedures for when state gets corrupted during a failed apply. None of that exists. You write code, you deploy code. ARM handles the reconciliation. That's the model. The way this actually works is through incremental deployments. When you send a Bicep template to ARM, you're describing the resources you want to exist in a particular scope, a resource group, a subscription, whatever. ARM asks, what's already there? What do you want? What needs to change? Then it changes only the things that need changing. The responsibility shifts from the tool to the platform. Terraform says, I'm responsible for knowing what's deployed. You tell me what you want, and I'll figure out the delta. ARM says, I'm the control plane. I know what's deployed because I deployed it. You describe what you want, and I'll handle the rest. One model pushes state management responsibility onto the organization using the tool. The other model pushes it onto the platform, which is built to handle it. This is a structural advantage that compounds over time. You don't need a platform team to manage state. You don't need coordination protocols between teams sharing state. You don't need to partition state across environments and manage the boundaries. You don't need to worry about state lock contention when 3 teams try to deploy simultaneously. Each team sends code to ARM independently. ARM handles it. The trade-off is real. With Terraform, you get an explicit plan before you apply. You see exactly what's going to change. You can review it, you can approve it. With Bicep, you don't get that explicit plan, not in the same way. You get a what-if operation that shows you what would change, but it's not the same as a plan. It's a prediction based on live data, not a comparison between code and a static state file. That's the cost. You lose the explicit, reviewable plan. But you gain something harder to quantify. You gain alignment with how the platform actually works. You stop thinking about state as something you manage. You start thinking about code as a declaration that the platform reconciles. This architectural difference cascades into governance and security in ways that aren't obvious at first. The what-if operation, live diagnostics versus static plans. When you run Terraform plan, you're asking Terraform a straightforward question. What changed? But that question has a hidden complexity. Terraform compares three things. Your code, the state file, what's actually in Azure right now. It pulls the live data, it does a refresh, and then it compares all three to figure out what needs to change. This should work perfectly. In theory, the state file matches reality. In practice, it often doesn't. The state file is stale. Someone made a manual change in the portal last week. Another team member applied a different configuration through a script. A resource got deleted because of a failed policy enforcement. Maybe the network failed halfway through an apply and corrupted the state file. Now, the state file doesn't match Azure. So when Terraform runs plan, it's predicting changes based on data it doesn't trust. You see a plan that looks safe, you approve it, you apply it, and something breaks because the state file lied. Bicep doesn't have this problem because it doesn't maintain a state file. When you run what if in Bicep, you're asking a different question. What would change if I deployed this right now? Bicep talks directly to the ARM control plane. It sends your desired state. ARM responds with what currently exists. Bicep shows you the delta. That delta is based on live data pulled seconds ago, not cached data that might be stale by weeks. The difference sounds technical. It's not. It's the difference between a prediction and a live question. Terraform predicts. Bicep asks. One is based on potentially stale state. The other is based on reality as it exists right now. This matters most in drift detection. Drift, the gap between what your code says should exist and what actually exists, is inevitable. Someone makes an emergency change. A policy violation gets remediated automatically. A resource gets deleted accidentally. Any number of things can diverge your live infrastructure from your code. Terraform detects drift by comparing state to code, but if the state file is stale, it won't detect the drift correctly. You end up running scheduled drift detection jobs. Scan your infrastructure every 15 minutes, every hour, every day, hoping to catch inconsistencies. Large organizations run drift detection constantly because they can't afford for state to be wrong. It's operational labor that exists entirely because you're maintaining a separate source of truth. Bicep doesn't need drift detection jobs. Every deployment is a drift check against live reality. You deploy. ARM shows you what changed. That's your drift signal. You're always looking at current state because ARM is the control plane. It knows what's there. The more significant advantage appears when you layer in governance. Azure Policy is Azure's built-in enforcement engine. It evaluates resources against rules and can block deployments that violate policy. When a Bicep deployment hits the ARM control plane, ARM checks it against every policy that applies to that scope. If it violates policy, the deployment fails before anything changes. You see the policy violation immediately. Terraform doesn't have this integration. You apply a Terraform deployment, ARM accepts it, the resources get created, then Azure Policy runs its evaluation. If the resources violate policy, they get flagged as non-compliant, but the deployment already happened. You created resources that shouldn't exist, then discovered that afterward. The timing difference is real. Bicep prevents violations before they create resources. Terraform discovers violations after it's too late. This creates a practical difference in your deployment experience. With Bicep, you see fewer surprises. Your feedback loop is tighter. Your governance is integrated into the deployment process, not bolted on after the fact. With Terraform, you're managing policies as a separate concern from deployment. The integration with governance is where native tooling reveals its real advantage. The module ecosystem, reuse versus standardization. The promise of Terraform is reuse at scale. The Terraform registry has 20,000 community modules. 20,000 across 100 plus providers, AWS modules, Azure modules, Kubernetes modules, Datadog modules. You name the platform, someone wrote a Terraform module for it. The ecosystem is massive. The breadth is undeniable. Azure has something different. Azure verified modules. AVM, not 20,000 modules, maybe a few hundred carefully curated ones. Built by Microsoft, tested against Azure patterns, versioned, maintained. Opinionated about how you should deploy things. One is a marketplace, the other is a library of standards. The difference reveals itself when you try to use the modules. A Terraform module is designed to work generically. It abstracts away cloud-specific details so it can run on multiple providers. That sounds useful. In practice, it means the module is optimized for none of them. It implements the lowest common denominator, the features that work everywhere. It skips Azure-specific capabilities because they don't exist in AWS. It uses patterns that work across clouds, even if Azure has better patterns for that specific service. You get breadth, you lose depth. An AVM module is built for Azure specifically. It knows about Azure resource patterns. It knows about Azure naming conventions. It knows about Azure governance integration. It knows that when you deploy a key vault, you should enable purge protection. It knows you should configure diagnostic settings automatically. It knows about soft delete. It knows about RBAC best practices. These things aren't optional nice-to-haves. They're built in. This isn't just convenience. This is knowledge. Every AVM module encodes years of operational experience using that service at scale. It's not just a resource wrapper. It's a distilled version of what Microsoft and enterprise customers learned about operating that service responsibly. The hidden cost of Terraform's breadth becomes apparent when you try to maintain it. You inherit 20,000 modules, many of them outdated, some are abandoned, some have conflicting patterns, some use different naming conventions, some follow AWS best practices and translate poorly to Azure. You're trying to build consistency across a marketplace that has no consistency. So organizations create internal Terraform modules. They wrap the community modules. They add governance. They add naming patterns. They add defaults that make sense for Azure. Essentially, they build what AVM already is. They've added layers of abstraction trying to solve the generic module problem. They've rebuilt the solution that already exists in AVM. The organizational friction is subtle but cumulative. Teams spend time evaluating which module to use, which one is maintained, which one has better documentation, which one aligns with your patterns. You're making decisions about decisions that AVM eliminates. This doesn't mean AVM is perfect. The catalog is smaller. If you need something super niche, it might not exist. But for the core services, compute, networking, data, identity, AVM has you covered. And what's there is built on assumption that you're optimizing for Azure, not hedging for AWS. The ecosystem difference reflects a fundamental philosophy about tool scope. Terraform asks, what if you need to go anywhere? AVM asks, how do we optimize for here? One tool treats its platform as a negotiation, the other treats it as home. The choice between them isn't about modules, it's about whether your organization is maintaining tooling consistency across many platforms or building depth on one platform. If you're Azure only, AVM's opinionated approach saves engineering effort. If you're genuinely multi-cloud, Terraform's generic breadth makes sense. But most organizations that pick Terraform for multi-cloud optionality end up maintaining Azure-specific modules inside Terraform anyway. They're solving the generic module problem manually, which means they're paying twice. State management as governance infrastructure. The state file is more than a technical problem. It's also a governance artifact. When you maintain a state file, you're maintaining a ledger. That ledger records every resource you're managing. It records configuration. It records who deployed what and when. It records change history if you version the backend properly. It becomes the canonical record of your infrastructure. This is actually useful for governance. If an auditor asks what resources are under IRC management, the state file answers that question. If someone wants to know who deployed a particular resource, the state file, combined with your Git history and backend versioning, can tell you. If you need to prove that a specific configuration was in place at a specific time, the state file provides evidence. But that evidence comes at a cost. You have to secure the ledger. You have to version it. You have to back it up. You have to control access to it. You have to monitor who reads it and when. You have to ensure that the people who can modify it are authorized to do so. You have to handle the mechanics of change tracking. You have to figure out how long to keep history and when to archive it. That's not a state management problem. That's a data governance problem. You've created a critical data asset and now you have to govern it like one. Bicep inverts this. Instead of Terraform maintaining a centralized state file as the infrastructure record, Bicep delegates the record keeping to Azure. Azure activity logs become your audit trail. Every deployment gets logged, every change gets recorded with timestamps and principles. Every policy check leaves a trace. You can query what changed, who changed it, when it happened, and what the result was. This is governance that the platform provides natively. You don't have to build it, you don't have to maintain it. It's already there as part of how Azure operates. The difference is architectural. Terraform centralizes infrastructure decisions into the state file. The state file is the single point of record. Everything flows through it. If you need governance data, you're extracting it from the state. If you need audit trails, you're building them on top of state versioning and backend logging. You're layering governance onto the tool. Bicep distributes responsibility differently. The code defines intent. Azure enforces reality. The audit trail lives in Azure's logs, not in a separate artifact. The governance happens at the platform level, not at the tool level. This creates a separation of concerns that matters operationally. With Terraform, your governance team has to understand the state file. They have to understand which state backend you're using. They have to understand who can access it. They have to design policies around state mutation. They have to ensure that state modifications go through the proper change control process. Your governance is entangled with tool mechanics. With Bicep, your governance team works with Azure natively. They configure Azure policies. They set up RBAC. They enable activity logs. They design role-based access to subscriptions and resource groups. They're using tools they already understand for managing cloud resources. Bicep is just the authoring layer. The compliance implications shift accordingly. If your audit requirements demand proof of change control, Terraform's explicit state tracking gives you that. You can version the state, lock changes behind approvals, and maintain a complete change log. If your audit requirements demand role-based access and activity logging, Bicep's reliance on Azure's native audit capabilities satisfies that. You're not managing a separate security domain for infrastructure code. Different organizations have different compliance needs. Some care deeply about an explicit versioned record of infrastructure decisions. Some care about proving that all changes went through proper RBAC gates and left audit trails. Terraform excels at the first requirement. Bicep leverages Azure's strength at the second. Understanding these governance models reveals where operational complexity actually lives. It's not just about managing state. It's about how you want infrastructure governance to work in your organization. Do you want a dedicated governance system, or do you want governance to flow through your existing platform controls? That's the real choice. The drift detection reality check. Drift is inevitable. It's not a failure mode. It's not something you prevent. It happens because organizations don't exist in a steady state. Someone deploys a patch to a server through the portal because waiting for code review took too long and the vulnerability was critical. A developer spins up a test database to debug something and forgets to tear it down. A policy violation gets auto-remediated, changing a configuration you didn't realize was non-compliant. A resource gets deleted by accident and restored from backup, but the state file wasn't updated. Any of these things causes drift. The infrastructure you're managing diverges from what your code says should be there. How you handle that divergence determines whether drift becomes a liability or just a fact of life. With Terraform, drift is a problem that requires management. When someone makes a change outside Terraform, any change, no matter how small, the state file becomes stale. The state file now claims something is configured one way, but Azure has it configured differently. The next time you run Terraform plan, Terraform is confused. It's comparing code against a state file that doesn't match reality. It doesn't know if the discrepancy is intentional or a mistake. So it either proposes to overwrite the live change, or it does nothing, and now you have two versions of the truth floating around. You can't leave drift unresolved because it breaks your ability to trust Terraform's plans. So you run drift detection. Large organizations don't do this manually. They run scheduled jobs. Every 15 minutes, every hour, every day, depending on how much they care, they scan the live infrastructure and compare it to the state file. They generate a drift report. They show teams what changed outside Terraform. Then they either update the state file to match reality or run Terraform apply to overwrite the changes. This is operational work. It's time. It's engineering. It's infrastructure you have to maintain to keep Terraform working correctly. Bicep doesn't have this problem in the same way, because Azure is the source of truth, not the code. When you deploy Bicep, you're sending a desired state to ARM. ARM looks at what's currently deployed. ARM figures out the gap. ARM changes only what needs changing. There is no state file getting stale. There is no comparison between two versions of the truth. But drift still happens. Someone still makes a change outside Bicep. A resource still gets modified manually or through another automation system. The infrastructure diverges from your code. The difference is what that means operationally. With Bicep, drift doesn't break your ability to deploy safely. Your next deployment will still work correctly because you're always asking ARM, what's actually there right now, not what's in my cached state file? The drift gets reconciled during the next deployment. You don't need scheduled drift detection jobs running continuously. You don't need a separate system to keep the state consistent. You deploy. ARM handles it. There's still visibility if you want it. Azure activity logs show what changed. Azure Resource Graph can show you current state. But you're not managing drift as an operational burden. You're observing it as a side effect of how the system works. The difference becomes acute in large organizations. A Fortune 500 company running Terraform might have dozens of drift detection pipelines running constantly, thousands of resources, multiple clouds, teams making changes across different systems. The drift detection overhead is substantial. You're running jobs just to keep Terraform's understanding of reality from diverging too far from actual reality. The operational burden reveals where Terraform's explicit state becomes a liability. You've built an elaborate system to manage the gap between what the state file claims and what's actually deployed. The system works. But it's work, and that work is only necessary because you chose a tool that requires it. The human factor compounds this. Teams make emergency changes. It's 3 a.m. and production is down and nobody has time to wait for code review and pipeline validation. So someone fixes it directly. Terraform now has a problem. That drift detection job will find it tomorrow. But today your state is wrong. Human behavior is inevitable. Tools that require teams to fight their own instincts create friction. Azure Policy Integration, native enforcement versus bolted-on controls. Azure Policy is Azure's governance engine. It evaluates resources against rules, it can enforce configurations, it can audit compliance, it can even remediate violations automatically in some cases. It's the mechanism that prevents teams from deploying things they shouldn't deploy. It's where your compliance requirements become actual constraints in the system. The question is, when does that enforcement happen? With Bicep, it happens before your infrastructure exists. When you send a Bicep template to ARM, something specific happens before any resources get created. ARM evaluates your deployment against every Azure policy that applies to that scope. If your deployment violates policy, the deployment fails. It doesn't create resources and then discover the violation. It stops beforehand. You see the policy violation immediately. You fix your code. You deploy again. The feedback loop is tight. This is pre-flight validation. It's prevention. Terraform doesn't work this way. You write your Terraform code. You run Terraform apply. Terraform talks to the Azure APIs and creates the resources. The resources exist now. After they exist, after Terraform is done, Azure policy evaluates them. If they violate policy, the resources become non-compliant. But they're already created. You have to delete them and rewrite your code. Then you have to apply again. The timing is different. The operational experience is different. Here's where this becomes real. Imagine you have an Azure policy that requires all storage accounts to have encryption enabled. With Bicep, if your template tries to create a storage account without encryption, the what-if operation fails before you deploy. You see the error. You add the encryption configuration, you deploy again, and it works. You never created a non-compliant resource. With Terraform, you create the storage account without encryption. It exists for a moment, then Azure policy flags it as non-compliant. Now you have a non-compliant resource in production. It might get automatically remediated if your policy is set up that way. Or it might just sit there marked as non-compliant until someone notices. Either way, the resource existed in a bad state before governance caught it. One prevents the violation. One discovers it after it happens. The difference multiplies across your organization. Teams deploy infrastructure constantly. If every deployment creates resources that might be non-compliant before governance catches them, you're creating compliance incidents continuously. You're managing the aftermath instead of preventing the problem. Bicep's native integration with Azure policy means governance is built into the deployment process. Policy definitions, initiatives, and assignments are resources you define in Bicep. They're not bolted on afterward. They're part of your infrastructure code. You version them, you test them, you deploy them alongside your other infrastructure. Governance becomes part of how you define systems, not a separate system that checks your work after the fact. Terraform's integration with Azure policy still works, but the policy itself is separate. You define your infrastructure in Terraform. You define your policies somewhere else. Through the portal, or through Terraform using the Azure policy definition resource, or through another tool entirely. The policies exist, they apply, but they're not tightly integrated with your deployment workflow. They're a separate concern that happens to run against your resources. Some organizations bridge this gap with external policy engines. Sentinel if you're using Terraform Cloud, OPA if you want an open source option. These are policy as code engines that evaluate your Terraform plans before they apply. They add that prevention layer, but they're another tool. They're another system to maintain. They add complexity. When Azure policy violations surface after a deployment, there's also a cost to fixing them. You have to update your code. You have to redeploy. If the policy has a remediation action, resources might get automatically fixed, but you still had a moment of non-compliance. You still had resources in a bad state. In regulated industries, that moment might require documentation. It might require incident reporting. It might trigger audits. Fewer failed deployments, faster feedback, tighter control. That's what you get when governance is integrated into the deployment platform itself, not bolted on afterward. The practical impact is that Bicep teams spend less time fighting compliance. Terraform teams spend more time managing the gap between code validation and governance enforcement. Both deployments eventually become compliant. The mechanisms ensure that. But the path there is different. One prevents violations, one discovers and remediates them. Which model you prefer depends on your tolerance for non-compliant resources existing momentarily and your willingness to maintain external policy engines. Both are valid choices. Neither is categorically better, but they're structurally different in how they handle governance. The cost of operational complexity. Here's what nobody quantifies clearly when they're pitching Terraform. The infrastructure you build to run Terraform isn't free. It has cost, it has operational surface area, it has failure modes. Every component you add to make Terraform work reliably introduces another thing that can break. You need a remote backend. That's a storage account or S3 bucket or Terraform Cloud subscription. That backend needs encryption. It needs versioning. It needs backup. Someone has to monitor it. If the backend goes down, Terraform can't work. If the backend gets corrupted, Terraform can't work. You've added a critical dependency. You need locking. Blob leases or DynamoDB tables or some other mechanism to prevent concurrent corruption of the state file. Locking adds latency. Locking can time out. Lock timeouts are their own class of incident. One engineer's Terraform run didn't finish properly. The lock didn't clear. Now everyone else is blocked. Someone has to manually clear the lock. That's operational work. You need encryption, at rest, in transit, with key management, with access policies. Multiple teams probably need access to different state files, so you're managing RBAC for the backend. Add a second cloud provider, and you're managing encryption and RBAC in both places. You need monitoring and alerting, state backend performance, state backend availability, concurrent lock attempts, failed deployments that leave locks in a bad state. These don't monitor themselves. You're adding observability infrastructure. Each of these components is necessary. None of them are optional if you want Terraform to work reliably, but collectively they represent operational complexity that exists only because you chose to maintain an external state file. State corruption happens despite all this. Concurrent runs sometimes don't coordinate properly. Network failures interrupt applies midstream. Misconfigured lock timeouts cause deadlocks. When the state file gets corrupted, recovery is manual. You're restoring from backup. You're manually editing the state file with Terraform state commands. You're verifying that the state matches reality. If you mess this up, you delete production resources by accident. This is not theoretical. This is what happens in organizations large enough to have Terraform at scale. The real cost emerges when you ask, who runs this? Someone has to be the Terraform person, or more accurately, someone has to be the platform engineering team that owns Terraform infrastructure. In small organizations, that's one person. In medium organizations, that's a team of 2 or 3. In large organizations, that's a full platform engineering group. Why? Because Terraform requires operational oversight that regular infrastructure doesn't. You're not just deploying things, you're managing the system that manages deployments. You're tuning back-end performance, you're responding to log failures, you're recovering from state corruption, you're managing authentication to the back-end, you're updating provider versions, you're maintaining Terraform modules, you're handling questions about, can I do X with Terraform? This is invisible to executives who see we're using IAC and assume they've scaled their infrastructure automation. They haven't. They've built a second infrastructure that requires dedicated engineering to operate. Bicep doesn't have this problem. Azure handles state. It handles consistency. It handles locking. It handles recovery. Your responsibility is the code. Azure handles everything else. This doesn't require a platform engineering team. It requires people who understand Azure and can write Bicep. That's a different skill set. A smaller team can operate Bicep effectively because the operational complexity is delegated to the platform. This has organizational implications. Organizations using Terraform need platform engineering people. Organizations using Bicep can distribute Terraform responsibilities across standard Azure operations teams. The difference in headcount is real. The difference in hiring difficulty is real. Smaller teams can operate Bicep effectively with standard Azure skills. Larger teams running Terraform have to hire people who specialize in Terraform operations. That's a rarer skill set. It's harder to hire for. It's more expensive. The hidden cost of Terraform isn't the tool. It's the people you have to hire to keep the tool working reliably. The skill set divergence. The skills Terraform demands are different from what Bicep demands. And that difference matters more than most organizations realize when they're evaluating which tool to adopt. Terraform expertise requires understanding several layers. You need to know HCL, the Terraform language. You need to understand how providers work and how to evaluate them. You need to understand state management patterns. You need to understand how to structure modules for reuse across multiple clouds. You need to know how to handle provider versioning and dependency management across an ecosystem of 100+ providers. You need to troubleshoot state corruption and log failures. You need to design back-end strategies that work across different cloud providers with different authentication mechanisms. This is a complete skill set. It's also a tool-focused skill set. You're becoming an expert in Terraform. You're becoming skilled at orchestrating multiple clouds through a single abstraction layer. You're becoming good at the meta task of managing a system that manages infrastructure. Bicep expertise is different. You need to know Bicep syntax, which is simpler than HCL. You need to understand Azure Resource Manager, how it actually works, what it does, what it can and can't do. You need to understand ARM templates because Bicep compiles to ARM. You need to know Azure services deeply. You need to understand RBAC in Azure. You need to understand how Azure policy works. You need to understand networking in Azure, identity in Azure, security in Azure. You need to understand what each Azure service actually does and how it integrates with other services. This is also a complete skill set, but it's a platform-focused skill set. You're becoming an expert in Azure. You're becoming skilled at using the platform's capabilities effectively. You're becoming good at the actual task of deploying infrastructure. Here's where the portability myth appears. People assume Terraform skills transfer. You learn Terraform. You can use it on AWS, Azure, and GCP. You can move between clouds. Your skills are portable, but they're only portable at the tool level. The moment you move to a different cloud, your code doesn't move. Your architectural knowledge doesn't move. You know how to write Terraform. You don't know how AWS actually works or how GCP actually works. You have to learn the services again. You have to learn the resource patterns for each cloud. You have to learn the naming conventions and best practices for each ecosystem. So you're portable, but your infrastructure knowledge isn't. Someone with deep Bicep and Azure expertise is the opposite. They can't move to AWS and take their Bicep skills with them. Bicep only works on Azure. But their knowledge of how Azure works, how to design systems on Azure, how to use Azure's native capabilities effectively, that's valuable and durable. That expertise ages well. That person is genuinely expert in Azure, not generically competent on multiple clouds. The hiring market reflects this. Terraform expertise is more widely known. More people have used it. More people can show you Terraform code on their resume. So finding people who know Terraform is easier. They're more common. But common skills are cheaper. They're easier to replace. The market commoditizes skills that many people have. Bicep expertise is rarer. Fewer people have worked with it deeply. The people who have tend to be Azure-focused, which means they've invested in learning the platform. That's harder to replace. That expertise is less commoditized. And the market pays better for skills that are harder to find. This creates a career trajectory question. Do you want to be the person who's good at orchestrating infrastructure across multiple clouds? Or do you want to be the person who's genuinely expert in one cloud and can design sophisticated systems on that platform? The second path tends to pay better long-term. Because you're not maintaining tool expertise, you're building platform expertise. That compounds, that becomes increasingly valuable as your cloud grows. Team alignment follows the same pattern. Your Terraform skills align with your tool. Your Bicep skills align with your infrastructure. Where you invest matters. The OpenTofu question, when licensing becomes governance, this is where your ISC choice stops being just a technical decision. In 2023, HashiCorp changed Terraform's license. They moved from MPL 2.0, a permissive open source license that lets anyone use the software for anything, to the business source license. BSL is a source available license that restricts commercial competitive use. You can read the code. You can't build a competing product on top of it. You can't use it to deliver infrastructure as a service as a business unless you pay HashiCorp for a commercial license. The community responded by forking. OpenTofu is that fork. It's the same code base Terraform was before the license change. Same HCL syntax, same provider ecosystem, same state model, same everything. The only difference? It's governed by the Linux Foundation as an open source project under MPL 2.0. That license is OSI approved. It means anyone can do anything with the code without restrictions. By 2026, OpenTofu is capturing a meaningful piece of new infrastructure projects. Estimates put it at about 35% of new IIC projects, up from roughly 10% in 2024. That's not a small number. That's a structural shift happening in real time. The governance change is what drives this adoption, not feature parity. OpenTofu is technically equivalent to Terraform at this point. They're close enough that switching between them is straightforward. But the licensing difference changes who controls your infrastructure orchestration tool. With Terraform, HashiCorp, now owned by IBM, controls what happens next. If they change the license further, if they decide to monetize features you currently use, if they sunset community providers in favor of paid ones, you're dependent on a corporation's strategic decisions. That dependency is fine if you trust the corporation and their incentives align with yours. But some organizations don't want that dependency. EU procurement laws increasingly prefer OSI-approved licenses for critical infrastructure software. Governments want to know they can fork the tool if they need to. They want to know they're not dependent on a vendor's goodwill. They want legal certainty that the tool will always be available under the same terms. OpenTofu provides that. Terraform doesn't. Regulated industries care about this too. Financial institutions, healthcare organizations, and utilities are moving toward OpenTofu for new projects, specifically because of the licensing model. They want open source guarantees, not source available arrangements. It's not that Terraform is bad, it's that they want legal certainty about their tooling. This creates an interesting tension. Organizations with substantial existing Terraform investments keep using Terraform. Migration is expensive. Migration is disruptive. The licensing model isn't a blocker if you've already built your platform on Terraform. You'll probably keep running it. But new projects increasingly start on OpenTofu. Organizations are deliberately choosing to adopt OpenTofu for greenfield infrastructure to avoid creating new dependencies on BSL licensing. Some organizations are running both, Terraform for legacy systems, OpenTofu for new ones. They're hedging, they're keeping optionality. This dual-engine approach is becoming standard in larger organizations. You maintain what you have. You build new things with what you prefer strategically. Bicep sidesteps this entirely. Bicep is MIT licensed. MIT is permissive. It's open source without restrictions. There's no license conversation. There's no governance risk. Microsoft publishes the code. You use it. If Microsoft ever changes course, the last open source version will be usable forever under the MIT license. That's not theoretical protection. That's how open source licensing works. This licensing clarity is becoming a competitive advantage for Bicep. Organizations evaluating IAC tools are now asking licensing questions upfront. Is this tool going to be free forever? Can we fork it if we need to? Can we build on top of it without legal risk? Terraform's answer is no. OpenTofu's answer is yes. Bicep's answer is yes. That's not a technical difference. That's a strategic difference. Your IRC tool choice is now a governance decision. It's about long-term control. It's about whether you're comfortable being dependent on a vendor's licensing model or whether you want the certainty that open source provides. Neither choice is wrong, but it's a choice your board and your legal team should understand. Because unlike a technical tool evaluation, licensing has consequences that last for years. The multi-team coordination problem. The moment you add a second team is when the state file problem becomes a coordination problem. In a small organization, one team owns Terraform. They deploy infrastructure. The state file sits in a backend. Nobody else touches it. This works. Life is simple. Then your organization grows. You hire a second platform team, a networking team, a security team. Different teams need to deploy different resources. They all need to touch the same infrastructure. Now they all need to share access to the same state file. This is where things get complicated. Terraform has workspaces to handle this. You can have separate state files per environment, dev state, staging state, prod state. Each workspace is isolated. Teams working on dev can't accidentally corrupt the prod state. And that's helpful, but it's only isolation at the environment level. Within a single environment, if multiple teams are deploying, they're still sharing a state file. Team A is deploying networking changes. Team B is deploying compute resources in the same environment. Both are talking to the same state file. If they run Terraform apply at the same time. The locking mechanism is supposed to prevent corruption. One applies first, the other waits for the lock to clear, then it applies. In theory, this works perfectly. In practice, timeouts happen. Network failures happen. Locks don't clear cleanly. One team's apply gets interrupted midway through, leaving the state file in an inconsistent state. The lock doesn't clear. Now the other team is blocked. Someone has to manually clear the lock. That's operational work. That's someone getting paged at 3 a.m. because a lock didn't clear cleanly. That's troubleshooting state corruption, while the rest of the team is blocked waiting for their deployment. State locking prevents corruption, but doesn't prevent logical conflicts. Team A and Team B are both applying changes to the same resource group. They're not modifying the same resource, they're modifying different things. But they're both talking to the same state backend, and something in that coordination goes sideways. Maybe Team A's change depends on a network configuration that Team B is also modifying. Maybe Team A creates a subnet that Team B tried to create at the same time. The resources get created, the state file gets updated, but now the intended configuration is wrong because the teams didn't coordinate their changes. You can't prevent this with better locking. You prevent this with process. Teams have to coordinate. They have to know what the other teams are doing. They have to schedule their deployments so they don't collide. That's operational overhead. That's meetings. That's change windows. That's friction. The coordination overhead grows exponentially as you add teams. 2 teams need to coordinate deployments occasionally. 3 teams need more coordination. 5 teams need constant coordination. 10 teams need a whole separate coordination function just to make sure deployments don't collide. Bicep doesn't have this problem because there's no shared state to coordinate around. Each team sends their Bicep code to ARM independently. Team A deploys, Team B deploys. They're both talking to the same control plane, ARM, but they're not fighting over a shared state file. ARM figures out what each team is asking for. ARM figures out if there are conflicts. ARM resolves them according to the order the requests arrive. Teams don't need to coordinate deployment windows. Teams don't need to schedule their changes. Teams don't need to avoid stepping on each other. Team autonomy changes operationally. Smaller teams can own their infrastructure without global coordination. A team can decide to deploy infrastructure on Tuesday without checking whether another team is deploying Wednesday. They just deploy. ARM handles it. Scaling becomes a different problem. With Terraform, scaling means managing coordination overhead. You're adding process, adding meetings, adding communication channels. The operational burden grows. With Bicep, scaling means adding more teams. The platform handles the concurrency. The coordination overhead doesn't grow because there is no shared state to coordinate. This coordination complexity becomes critical when you're running large organizations. When you have dozens of teams deploying to the same Azure environment. When you have infrastructure that multiple teams depend on. When you need autonomy but can't afford coordination meetings. One model centralizes control into the state file, which creates coordination requirements. The other distributes control to the platform, which eliminates them. The regulatory and audit alignment. When regulators show up, they want one thing above all else: proof. They want to know who changed what, when it happened, why it happened. They want a traceable path from decision to deployment to current state. They want evidence that the change went through the proper controls. They want to know that whoever made the change was authorized to make it. That's audit. That's the currency of regulated industries. Terraform and Bicep answer these requirements differently. Terraform's advantage here is explicit. The state file is a ledger. It records every resource Terraform is managing. It records the configuration of each resource. If you version your state backend properly, and you should, you have complete version history. You can see what the state file looked like 6 months ago. You can see what changed between then and now. You can see who made each change by cross-referencing with your Git history. The state file becomes evidence. It becomes proof that you're managing infrastructure according to code, not making random console changes. This is what regulators want to see. When a compliance auditor asks, "How do I know this database is encrypted?" you can show them the state file. There it is. Encryption enabled. This is the configuration that Terraform deployed. This is when it was deployed. This is who approved the change. The state file is your audit artifact. Terraform's explicit change tracking also maps to compliance frameworks. SOX requires that critical system changes go through change control. The state file plus Git history proves that. HIPAA requires that infrastructure changes be auditable. The state file and version history provide that. PCI DSS requires that access to critical systems be controlled and logged. The state backend locking and access control demonstrate that. For regulated industries, Terraform's model aligns well with how compliance frameworks think about infrastructure. But there's a cost to this alignment. You have to actually build and maintain the audit trail. Your state backend has to be versioned. Your access control has to be logged. Your state file has to be secured against tampering. These aren't automatic. They're things you have to deliberately configure and operate. If you don't, you have no audit trail. You have a tool that looks like it's managing infrastructure, but you have no proof that the changes actually went through proper controls. Bicep handles audit differently. Bicep doesn't maintain a state file, so there's no state-based audit trail. Instead, your audit trail comes from Azure itself. Azure activity logs record every deployment. They record who initiated it, when it happened, what resources were created or modified. Azure logs are tamper evident. They go to Azure Monitor and Log Analytics. which are themselves auditable systems. You're not relying on Terraform's versioning, you're relying on Azure's logging infrastructure. This sounds less explicit than Terraform's state-based tracking, but it's actually more robust. Azure activity logs are continuous. They're not dependent on your configuration. They don't require you to version anything. They flow to a centralized logging system that's designed for audit. They're encrypted. They're access controlled. They're compliant with every major framework because they're part of Azure's own compliance infrastructure. Azure Policy Compliance adds another layer. When you deploy with Bicep, Azure Policy evaluates the deployment against every policy that applies. That evaluation is logged. You have a record of what passed and what failed. You have proof that governance was enforced. For regulatory alignment, this changes how you satisfy compliance requirements. Instead of proving that you're using IAC correctly, which requires you to maintain a proper state backend and versioning system, you're proving that you're using Azure correctly. You're using built-in logging and policy enforcement. Both are part of Azure's compliance story. Multi-jurisdiction complexity exposes another difference. If you operate in Europe and North America, policies differ, data residency laws differ, audit requirements differ. Terraform's state model is the same everywhere. You build the same state management system in Europe as you do in North America, but compliance requirements are different. You end up with a state management system that works everywhere but satisfies compliance differently everywhere. Bicep uses Azure's regional infrastructure, Azure's logging, Azure's policy enforcement, Azure's compliance certifications. They're regional. Your audit trail respects jurisdictional boundaries because it's built on Azure's boundaries. This becomes critical when auditors ask whether your infrastructure matches your declared compliance posture across multiple jurisdictions. Terraform's answer requires you to prove it through state versioning and access control. Bicep's answer is that you're using Azure's native compliance infrastructure, which handles multi-jurisdiction complexity as part of how the platform operates. Neither requires you to choose between control and compliance, but they distribute the responsibility differently. The AI and agentic automation layer. By 2026, AI is touching infrastructure code in ways that were purely theoretical a few years ago. AI agents can read infrastructure requirements and generate Bicep or Terraform. AI can review your infrastructure code and suggest improvements. AI can identify resources that aren't compliant with policies. AI can even propose changes automatically. Some organizations are beginning to experiment with AI that doesn't just suggest changes but actually initiates them, creates the pull request, runs the tests, waits for approval. This is happening. It's not coming. It's here now. But there's a massive trust gap. Research from 2026 shows that only about 34% of organizations say they'd trust an AI agent to make autonomous production infrastructure changes. And when you dig into why, the answer is consistent. Lack of guardrails. Teams don't know how to constrain what the AI can do. They don't know how to prevent it from making dangerous changes. They don't know who's responsible if the AI generates a change that breaks production. That's the guardrail problem. How do you let AI augment your infrastructure automation without losing control? How do you say, yes, you can generate this code, but no, you can't do that? How do you implement policy enforcement that applies equally to AI-initiated changes and human-initiated changes? Terraform and Bicep answer this differently, and the difference matters more as AI becomes more involved in IRC authorship. With Terraform, the external control layer is policy as code engines. Sentinel if you're using Terraform Cloud. OPA, Open Policy Agent, if you want an open source option. These engines evaluate Terraform plans before they apply. If the plan violates policy, it fails. The AI can generate code, but the policy engine validates that code before it runs. The guardrail is external. It's bolted on, it works, but it's another system to maintain. Bicep's guardrails are native to the deployment process. Azure Policy evaluates every deployment against every policy that applies to that scope. AI-generated code hits the same policy validation that human-written code hits. The guardrail is built in. It's part of the platform. It doesn't require a separate engine. It doesn't require a separate configuration. It just works. This distinction becomes critical when you think about governance at scale. If AI is going to generate infrastructure changes, you need confidence that those changes can't violate governance. With Terraform, you have to build that confidence through policy as code engines. You have to ensure those engines are running. You have to ensure they are configured correctly. You have to maintain them. With Bicep, that confidence is inherent to how the system works. Attribution and liability add another layer to this problem. When a human writes code, they're responsible for it. They review it, they approve it. There's a clear chain of accountability. When AI writes code, who's responsible? Did the AI make a bad decision? Did the human who approved it miss something? If a failure happens, who's on the hook? This is partly a legal question, but operationally it drives how you structure your approval flows. Some organizations are implementing tiered approval systems. Low-risk changes, adding a tag, modifying a non-critical resource parameter can be approved quickly. High-risk changes, modifying network policies, changing database settings, creating new service principles, require multiple approvals and might require human review, even if an AI suggested them. Terraform's model doesn't enforce this. You have to build the approval logic into your pipeline. Bicep's model integrates with Azure RBAC and Azure Policy, which naturally encode risk tiers into role-based access. A junior engineer might only be able to deploy to dev. A senior engineer can deploy to prod. That risk structuring is native to the platform. The future of infrastructure automation is AI augmented. But the tool's governance model determines how safely AI can participate. Terraform requires you to bolt on governance. Bicep has governance built in. But that's not a minor difference. That's an architectural advantage that compounds as AI becomes more involved in infrastructure authorship. The enterprise platform engineering reality. Platform engineering is the function that emerged when organizations realized they needed infrastructure abstraction. Instead of every team managing their own cloud accounts and making their own architectural decisions, platform teams build frameworks. They publish self-service infrastructure. They encode standards into templates. They provide safe rails that let application teams deploy quickly without breaking governance. The IAC tool choice becomes critical here because the platform team is choosing what abstraction layer sits between application teams and the cloud itself. Terraform often becomes the platform orchestration engine in this model. A platform team builds a Terraform module library. They create modules for networks, for compute, for databases, all the building blocks that application teams need. Application teams consume those modules. They write simple Terraform code that stacks modules together. The platform team owns the complex infrastructure patterns. The application teams get self-service without having to understand the platform deeply. Terraform's reach across multiple clouds makes it attractive for platform teams that operate heterogeneously. You have a few services on AWS, a few on Azure, a few on GCP. The platform team wants one language, one tool, one way of managing infrastructure across all of them. Terraform provides that. But Terraform at platform scale introduces the state coordination problem we discussed earlier on steroids. The platform team has central modules. Application teams are using those modules. Everything flows through the same state backend. The platform team is deploying foundational infrastructure. Application teams are deploying on top of it. If the platform team's state and the application team's state collide, you have cascading failures. The coordination overhead becomes the platform team's job. Bicep's role in platform engineering is different. Bicep is typically used for landing zones and foundational infrastructure patterns. A platform team designs landing zone templates in Bicep. These are predefined Azure subscription structures, networks, policies, logging, baseline resources. When a new team needs infrastructure, they get a landing zone. The Bicep template creates the entire zone automatically. Application teams then deploy their own infrastructure on top of the landing zone. They might use Bicep, they might use something else. But the foundational architecture comes from the platform team's Bicep templates. This creates a cleaner separation. The platform team owns the landing zone, the Azure-specific foundational pattern. Application teams own their services on top of that pattern. They're not fighting over a shared state file. They're deploying into a predefined structure. Governance is baked into the landing zone itself. Networks are pre-segmented, logging is predefined, policies are configured, application teams inherit all of that. The hybrid pattern is becoming standard in enterprise platform engineering. Terraform handles orchestration across multiple clouds. It handles the meta layer, the platforms that span different infrastructure. Bicep handles the Azure layer specifically. You're using both because they're solving different problems at different architectural levels. A real example, a platform team at a large organization might use Terraform to orchestrate landing zones across Azure, AWS, and GCP. Each cloud has a different orchestration because the clouds are different. But within Azure, they're using Bicep templates for the Azure-specific landing zone structure. Application teams deploy Bicep on top of that. This distributes complexity appropriately. Terraform manages the complexity of multi-cloud orchestration. Bicep manages the complexity of being native to Azure. Neither tool is responsible for both. Neither tool is stretched beyond its architectural purpose. Module reusability works at both levels. The Terraform modules are cross-cloud abstractions. The Bicep modules are Azure-specific patterns. Teams consuming these modules don't have to understand the distinction. They just use what the platform team provides. Governance enforcement happens at both levels too. Terraform policy as code at the platform layer ensures that what gets orchestrated across clouds follows standards. Bicep-based Azure policy enforcement at the Azure layer ensures that what gets deployed within Azure follows Azure governance. Governance isn't competing with itself. It's working at appropriate scopes. Self-service becomes easier when the platform provides structure. Instead of teams wrestling with the full complexity of multi-cloud orchestration or Azure-specific networking, they're working within a framework. The platform team has already decided which patterns are safe. Teams pick a pattern and deploy. Governance is implicit in the structure. This is where platform engineering maturity lives, not in choosing one tool, but in structuring how multiple tools work together appropriately. Platform architecture decisions usually force this hybrid approach because no single tool is optimized for every layer of abstraction. The teams that mature past this recognize it and embrace it. The true cost of ownership calculation. The real cost of your IAC choice isn't what you pay for the software. It's what you pay to keep it running. Most organizations evaluate IRC tools based on license cost. Terraform is free, Bicep is free, the evaluation ends there. But this math ignores everything that actually costs money. Terraform requires infrastructure to operate. A remote backend, whether that's Terraform Cloud, an Azure storage account, or an S3 bucket, costs money. Not much individually, but it compounds. You're paying for storage. You're paying for redundancy. You're paying for backup retention. If you're using Terraform Cloud, you're paying their subscription fee. If you're using a custom backend orchestrator like Spacelift or Scala, you're paying their licensing costs. None of these are trivial when you multiply them across dozens of workspaces across multiple environments. Then there's the operational cost. Someone has to monitor the backend. Someone has to troubleshoot state corruption when it happens. Someone has to run backup and restore procedures. Someone has to manage access control to the backend itself. This isn't a one-time effort. This is ongoing operational overhead. Bicep's infrastructure cost is zero. Azure handles everything. You pay for the resources you deploy. You don't pay for the infrastructure that manages the deployment. But then consider the inverse cost. Bicep locks you to Azure. If your strategy shifts and you need to operate on multiple clouds, Bicep can't go with you. You'd have to migrate to a tool that spans clouds. That migration is expensive. That retraining is expensive. Terraform, even if it costs more to operate, at least preserves your optionality. And this matters only if multi-cloud is actually your strategy. If you say you're multi-cloud, but you're really 95% Azure, the cost of that optionality is money you're spending on insurance you don't need. If you're genuinely multi-cloud, running significant workloads on different platforms, the cost of switching away from Terraform is enormous. Skill development is a less obvious cost that compounds over years. If you choose Terraform, you're training your team on Terraform. That's courses, it's mentorship, it's time spent learning the tool rather than solving problems. If you choose Bicep, you're training your team on Bicep and deeper Azure understanding. The upfront training cost is similar, but the long-term payoff differs. Terraform skills are more widely available on the market. If you need to hire, you can find people who know Terraform, but those people aren't necessarily cheaper. They're actually more expensive because the skill is commoditized. Bicep expertise is rarer. When you find someone who knows Bicep deeply, they are usually genuinely expert in Azure. That costs more upfront, but it holds value longer. Migration costs should scare you more than they do. If you're running meaningful infrastructure on Terraform and you decide to move to Bicep, that's not a simple tool swap. You're rewriting infrastructure code, you're retraining teams, you're testing everything, you're managing risk during cutover. Large migrations take months. Large migrations cost 6 figures easily. Most organizations never actually do this migration because the cost is too high. This creates switching costs that affect your options going forward. You've already paid the cost to adopt Terraform. The cost to switch is so high that you'll live with Terraform even if a better option emerges. That's lock-in that comes from operational investment, not licensing. Incident response costs are real but often uncounted. When something breaks in Terraform, state corruption, locking issues, provider misbehavior, someone has to fix it. They have to understand state management. They have to know how to recover. They might have to restore from backup. Incident response for Terraform requires Terraform expertise. Bicep incidents are different. If a deployment fails, you're troubleshooting Bicep code or Azure behavior. You're not troubleshooting a state management system. That's a different cost profile. Audit and compliance costs depend on your regulatory requirements. Terraform's explicit state tracking can reduce audit cost if you're already maintaining state versioning and backend logging. Bicep's reliance on Azure's native logging might simplify audit if you're already instrumented for Azure compliance. The trick with true cost of ownership is that it's never just one number. It's the sum of infrastructure costs, operational overhead, skill acquisition, optionality preservation, migration risk, incident response, and compliance alignment. Weight each factor differently depending on your strategy. An organization committing long-term to Azure probably weighs Bicep's simplicity more heavily. An organization deliberately building multi-cloud might accept Terraform's operational burden for that flexibility. The cost calculation reveals where your long-term investment should actually flow, not toward the cheapest tool, toward the tool whose operational model aligns with how you actually work. The decision framework. When to choose which tool. Here's where all of this converges into an actual choice. You can't choose based on which tool is better. Both are mature, both work, both have distinct trade-offs. The choice is about which trade-off aligns with your actual situation, not the situation you want to be in, the one you're actually in right now. If your infrastructure lives exclusively in Azure, the logic is straightforward. Bicep is faster, Bicep is simpler, Bicep integrates natively with governance. You don't get multi-cloud reach, but you're not using multi-cloud reach. The operational simplicity pays dividends immediately. Smaller teams can operate it, less infrastructure overhead, faster feature adoption. This is the default path for Azure-only organizations. But if you're running significant workloads on multiple clouds, that simplicity doesn't apply. You need one language, one tool, one deployment pattern that works across environments. Terraform or OpenTofu is non-negotiable here. You accept the state management overhead because the alternative, maintaining different ISC tools for different clouds, is even more complex operationally. The coordination overhead of managing multiple tools across multiple clouds exceeds the overhead of managing Terraform's state. Most large organizations end up somewhere between these poles. They're Azure first, but they have some workloads elsewhere, or they're genuinely multi-cloud. The answer often becomes hybrid. Terraform handles what spans clouds: the cross-cloud orchestration layer, the central governance, the things that touch multiple platforms. Bicep handles what's Azure-specific: landing zones, foundational patterns, Azure native services. They're not competing. They're solving different problems at different architectural levels. Your team structure matters more than most organizations realize when they're making this choice. If you have a centralized platform engineering team responsible for infrastructure across the organization, Terraform often makes sense. The platform team owns the complexity. They manage state, they manage coordination, they build the modules. Everyone else consumes what they provide. This concentrates the operational burden in one team, which can handle it. It also means that tool choice is a platform team decision, not a distributed team decision. But if your organizational structure is more distributed, different teams owning their own infrastructure, different business units managing different cloud accounts, the coordination overhead of shared state becomes unbearable. Bicep's stateless model suddenly becomes an advantage. Teams can deploy independently. They don't need global coordination. They don't need permission from a central platform team to deploy on Tuesday versus Thursday. That autonomy has real value in decentralized organizations. Regulatory requirements add another consideration that's often overlooked. If your audit function cares deeply about explicit change tracking, who changed what, when, and why, Terraform's state-based audit trail might align better with what auditors expect to see. The state file is a ledger. You can show it to auditors. Bicep's reliance on Azure's native logging works too, but it requires a different audit story. Neither fails compliance. But one might be easier to explain to your compliance function. Licensing is becoming a strategic question, not just a technical one. If your organization has a policy against business-sourced licensed software, and increasingly EU organizations and governments do, Terraform creates a problem. OpenTofu solves it. You get the multi-cloud reach without the licensing risk. If licensing doesn't matter to your governance, Terraform's maturity and ecosystem might outweigh OpenTofu's newness. If licensing is a constraint, OpenTofu is the obvious path. Feature velocity matters if you're in industries where new Azure capabilities are competitive advantages. If you operate in regulated industries, Azure releases compliance features first. New policy capabilities, new encryption options, new audit features, Bicep gets them immediately. Terraform's Azure provider gets them in weeks or months. That gap doesn't matter if you don't use early features. It matters enormously if you do. Your organizational maturity sets expectations too. Younger organizations, smaller headcount, less formalized processes, often benefit from Bicep's simplicity. Less infrastructure to operate, faster time to capability. Mature organizations with established platform teams can leverage Terraform's power and flexibility. They have the engineering capacity to manage it well. None of these signals point to one universal answer, but together they point to what matters for your specific context. The choice isn't about which tool is objectively better, it's about which model, which operational philosophy, which trade-offs aligns with your constraints, your strategy, and your team structure. Choose the tool whose burden you're willing and able to carry. That's how you avoid the trap. The governance metrics that matter. Here's what most organizations measure wrong. They measure IAC adoption, percentage of infrastructure deployed through code, percentage of teams using the tool. Adoption metrics are easy to calculate. They make you feel like you're making progress, but they're measuring the wrong thing entirely. If 90% of your infrastructure is deployed through ISC, but half of it violates your compliance policies, you haven't won. You've just automated the problems. You've made them scale faster. The metrics that actually matter are harder to track, but they reveal where your tool choice is genuinely impacting your business. Control coverage is the real metric. Of all your production resources, every VM, every database, every network, everything running in production, what percentage is actually under governance? Not deployed through code. Under governance, meaning it's being managed through approved patterns, it's passing policy checks, it's being monitored for drift. A team might deploy infrastructure through ISC, but if they're not integrating with Azure policy, if they're not running drift detection, if they're not gating deployments through approval workflows, then that infrastructure isn't really governed. It's just automated. The gap between deployment and governance is where risk hides. Drift metrics matter because drift is where governance breaks down in practice. You define a policy, you enforce it at deployment time, everything passes. 2 weeks later, someone makes a quick fix in the console. The policy is still active, but the fix didn't go through the approval process. Now you have a resource in a state that violates your intention, even though it technically complies with the policy. The real metric is mean time to detect that drift and mean time to reconcile it. If it takes 3 months to discover that a critical database lost its encryption configuration, your governance isn't working. If it takes a day, you're responding quickly to problems. Compliance metrics get at whether your governance is actually preventing bad things. Percentage of resources passing automated policy checks, not resources that you're hoping are compliant, resources that are actually passing validation. This surfaces which policies are too strict and which are catching real problems. It also surfaces whether your teams are working around policies instead of working within them. If compliance is 75%, you have a problem. Either your policies are too restrictive or your teams don't understand them. Either way, you're not actually governing. Incident metrics reveal the impact of your governance choices, number and severity of infrastructure-related production incidents. Infrastructure-related means incidents that happened because infrastructure was misconfigured, was deployed wrong, or violated a policy. The tool you choose and how rigorously you govern it directly impacts this number. A team deploying manually through the console has one incident rate. A team deploying through IAC with governance has a lower one. A team deploying through IAC without governance has a different rate entirely. The gap between incident rates tells you whether your governance investment is paying off. Cost metrics matter because the whole reason to have governance is usually to control spend. Infrastructure costs as a percentage of your cloud spend. Chargeback accuracy if you're allocating costs back to teams. If 40% of your infrastructure bill is going to resources nobody remembers creating, you have a governance problem. If teams can't be charged back accurately for what they're consuming, your cost allocation system isn't working. Audit readiness is the compliance metric that matters. When an auditor shows up and asks who deployed that database and when, how fast can you answer? How complete is the information? Can you trace the change from request through approval, through deployment, through current state? If that answer takes weeks, your audit trail isn't working. If you can answer in hours with complete information, your governance infrastructure is sound. Team velocity matters because governance can slow teams down if it's not designed right. Deployment frequency, lead time for changes, mean time to recovery from incidents. If governance makes it so that a simple configuration change takes 2 weeks to deploy, teams are going to find workarounds. The goal is governance that enforces control without killing velocity. The tools you choose and how you structure your governance determine whether you can achieve both. These metrics reveal where your tool choice is actually hitting the bottom line, not whether you're using a tool, whether the tool is making you faster and safer simultaneously. The 2026 landscape where the market is moving. The IAC market in 2026 is far different from what it was 3 years ago, and the trajectory tells you where things are going. Terraform is still the incumbent. It has the largest installed base. Most organizations running infrastructure at scale are running Terraform. But that incumbency is being challenged in ways that matter strategically. The licensing change to BSL created a fracture in the ecosystem that didn't heal. It created OpenTofu. It made organizations nervous about vendor control. It forced conversations about what happens if HashiCorp changes course again. Organizations with massive Terraform investments aren't going anywhere. Migration is too expensive, but that doesn't mean they're comfortable. Many are running OpenTofu for new projects specifically as a hedge. They're keeping their options open. They're saying, we'll maintain what we have, but we're not expanding our dependence on a single vendor's licensing model. Bicep adoption is accelerating in Azure environments, but it's accelerating differently than Terraform matured. Terraform grew through grassroots adoption, engineers choosing it because it solved their problem. Bicep is growing through organizational endorsement. Azure Verified modules aren't a community project. They're Microsoft-backed, enterprise-grade, tested standardization. They're what you use when you want the platform vendor's blessing. This matters because it signals confidence. Organizations are saying if Microsoft is backing these modules, we can standardize on them, we can build enterprise patterns on them, we can delegate the module ecosystem to Microsoft instead of maintaining it ourselves. The ecosystem itself is consolidating. Cloud providers used to have proprietary tools. AWS had CloudFormation, Google Cloud had Deployment Manager, Azure had ARM templates. These were vendor-specific, limited to that cloud. But the ecosystem realized that companies need consistent tools across their infrastructure. So the major cloud providers started supporting multiple tools. Terraform became a first-class citizen on all 3 major clouds. OpenTofu is following the same path. Even Bicep is now supported in enterprise orchestration platforms that used to be Terraform only. The tools themselves are converging too. Terraform and OpenTofu are now functionally equivalent at the core. They use the same language, they have compatible state. They're not diverging, they're staying aligned because they started from the same codebase. Bicep is its own thing, but it's competing in the same space. The feature gap that existed between Terraform and Bicep 5 years ago is much smaller now. Pulumi is emerging as a different approach entirely. Instead of a domain-specific language, Pulumi lets you write infrastructure in Python or Go or other general-purpose languages. If your team has Python developers, they can write infrastructure without learning HCL. This appeals to organizations where infrastructure is written by application teams, not specialist platform engineers. It's gaining traction, especially in companies where the skill set overlap is high. What all of this points to is platform consolidation happening across enterprises. Most mature organizations are moving toward multi-tool strategies, not because they can't make one tool work, but because different tools solve different problems. Terraform for cross-cloud orchestration, Bicep for Azure-specific patterns, Pulumi for teams that want general-purpose language infrastructure. They're not choosing one winner, they're choosing the right tool for each architectural layer. The real convergence isn't in the tools competing, it's in governance and policy as code becoming more important than the tool itself. You could run Terraform today and migrate to OpenTofu tomorrow, and your governance layer would mostly stay the same. You could layer Azure policy on top of either Bicep or Terraform. The policy engine is becoming what matters, not whether you're using Terraform or OpenTofu or Bicep. This is where the market is settling. Executives should pay attention because it means your tool choice matters less than your governance choice. And your governance choice matters more than your tool choice. The tools are good enough. The differentiator now is whether you can enforce policy and maintain control regardless of which tool runs underneath. Organizations that understand this ahead of time gain a strategic advantage. They're investing in governance infrastructure and treating tool choices as implementation details. They're building to be tool agnostic where it matters and tool specific where it doesn't. Understanding market movement helps you make decisions that age well instead of decisions you'll regret in 2 years when the landscape shifts again. The real trap and how to avoid it. The trap isn't choosing the wrong tool. That's what consumes every debate. Terraform versus Bicep. Which one wins? But the actual trap is different. It's choosing a tool without understanding the model underneath it. Both tools work. Neither is objectively wrong. But each embeds a philosophy about how you manage infrastructure. That philosophy has consequences that compound over years. Most organizations never explicitly choose which philosophy they're adopting. They pick what's popular or what their platform team recommends. Then they live with the consequences. Terraform's trap is that the state file becomes a system you're managing instead of a means to an end. You started wanting to deploy infrastructure. Now you're managing state backends, worrying about concurrent runs, troubleshooting log failures, maintaining version history. The tool you adopted to simplify deployment created operational work that often exceeds the original problem you were solving. The state file is powerful, but it's still an abstraction that requires operational care. Most teams spend more time managing the manager than managing the infrastructure. Bicep's trap is different. It's not overhead, it's optionality. You commit to Azure completely. If your strategy shifts, if you need to operate on another cloud, if you need multi-cloud consistency, Bicep can't go with you. You're locked in, not by license or contract, by architectural choice. That lock-in might never matter. But if it does, the cost is enormous. These aren't tool failures. They're natural consequences of the models underneath. Both work well if they align with your actual situation. Both fail hard if they don't. The real question isn't which tool is better. It's which operational model aligns with your team structure, your strategy, and your risk tolerance. If your strategy is Azure only for the foreseeable future, Bicep's lock-in isn't a trap. It's clarity. You're not giving up optionality you need. If your strategy demands flexibility across clouds, Terraform's state burden is acceptable. The alternative, separate tools, separate processes, separate skill sets, is worse. Avoiding the trap means measuring what actually matters. Don't measure adoption. Measure outcomes, control coverage, compliance pass rates, incident reduction, audit readiness. These metrics tell you whether your choice is working. If you're deploying through code but incidents aren't dropping, something is misaligned. The hybrid reality is most mature organizations use both tools, not because they couldn't make one work, because different layers need different approaches. Tools that look like competitors become complementary as infrastructure scales. Future-proofing means selecting tools that let you evolve without complete rewrites. If vendor lock-in prevents changing direction without years of migration, that's risk. If your choice is flexible enough to shift without massive effort, that's resilience. Invest in governance regardless of which tool you pick. Policy as code, automated compliance, infrastructure standards, these work with Terraform or Bicep or both. They're what controls your risk. The tool is secondary to governance quality. That clarity changes everything. The operational tolerance decision. The choice between Terraform and Bicep is ultimately a choice about operational tolerance. Terraform means you own orchestration, state management, complexity. You get explicit control and multi-cloud reach. You accept the burden of managing a system that manages infrastructure. Bicep means you own code, Azure owns state. You inherit platform constraints. You get simplicity and native integration. You accept being locked to one cloud. Neither is universally right. Both require trade-offs. The real decision is which trade-off aligns with your team, strategy, and risk tolerance. The market is moving toward hybrid approaches and governance-first thinking. Most organizations will eventually use multiple tools. Your next step, audit your current IRC state. Measure real operational costs, incident rates, audit readiness. Align your tool choice with your actual strategy. The best IRC tool is the one your team can operate reliably and evolve confidently. That's not the same tool for everyone. Find yours.